So this is a little bit about Guru and how you can impress your students is what basically we're going to be talking today about. A little stories on that. So the story goes like this. There is this old man who's standing on a roadside tea shop and is having chai, and there is two middle-aged people around, say 35 plus, riding on the bike. They're going fast, and all of a sudden, the pillion rider, the person on the back, just taps on his friend. Says, "Stop! Stop! Stop! Stop the vehicle!" He just comes to a screeching halt, stops the vehicle. Says, "Why do you want me to stop, there?" I said, "Yes, yes, you just get on, get on." And he just gets off and walks to the person who's standing in the tea shop. This old man having his cup of chai on a nice cold morning. He just procrastinates on his feet, touches his feet, and "Sir, namaste, sir. How are you?" He says like, "I'm fine. Who are you?" "Sir, was you might have forgotten me, sir, but how can I forget you, sir? You are my teacher. I am also a professor or a teacher now today, sir. That is only because of you." He says, "Good to know that you're also in the teaching profession. Excellent. What deed of mine impressed you or made you to become a teacher?" He says like, "Sir, do you remember that watch episode?" He says, "Yes." "I don't remember, son. I'm also kind of getting old. I don't remember a lot of things now. Can you just brush my memory up?" So he jogs. "I'll help you jog your memory, sir. Remember, one day in this school, there was in all the schools they have, and also in colleges, there will be at least one or two kids who show off. From an affluent family, they will, There is this kid who always does a lot of show off, and one day he wears a nice gold watch to the class. This is about, let's say, 8th standard, 9th standard kids, and he's like showing off big time, and people are getting upset. And quite a few people don't like him. People are upset, and all of a sudden, the class is going to be over. The school is going to be over. The rich boy screams, "Sir, sir!" "What is it, boy?" "Sir, somebody stole my watch." "Somebody stole your watch? How is it possible?" "I don't know, sir. Probably I just removed it to wipe off the sweat. I kept it here. It's gone. I lost it. It's a fantastic watch. My father will kill me. Please help me to get it, sir." It says, "Okay, fine, no problem. My dear students, I know all of you are very good. Our friend has lost his watch now. So what I'm going to do is I'm going to close the door. Nobody can leave. Please form a line. And I request all of you, whoever has taken it, to put the watch in there. This is the school where they wear blazers, like the Ooty schools or a lot of schools in Delhi and North India. They wear this jacket, blazer overcoat. So he says, put it in your jacket pocket or your coat pocket, and just keep quiet. So it goes on, and then the teacher walks, inspecting each and every jacket pocket, and then finally he gets the watch out, and then he says, "Okay, all of you," and before that he says, "All of you have to close your eyes. Once you stand in the line, close your eyes." So all of them have closed their eyes, and then the sir took the watch out, and then he said, "Okay, now we found the watch." And the guy says, "Oh, thank you, sir. Who took it?" He says, "Don't worry, doesn't matter." Okay. So he just lets everybody go home, and life is as usual. The next day, people are coming, is going. The gentleman who stopped the vehicle says, "That is the incident made me to become a teacher." He says, "Okay, well, what is that that impressed you so much?" It's not everybody became a teacher just seeing that. He said, "Sir, that is one thing that impressed me, and there is another thing that I've been searching to find you and ask you is this. Why is that after you knowing that I took the watch, you never said anything? You never called me, you never screamed at me, you never yelled at me, you never said this is wrong, you never advised me. Why, sir? Why didn't you do that? Can anyone take a guess? Why did the sir didn't say anything? The professor, the teacher did not scold that boy.
He might also closed his eyes.
Who's this?
I'm Sridevi, sir.
Sir, excuse sir, sorry to disturb sir. Sir, yeah, what ma'am have told, that's absolutely right, sir. Because I heard about the story, sir, earlier.
Okay, so if you have heard the story, you shouldn't break the, like the answer you shouldn't release. See, like Krishnakant is thinking the boy will realize. Okay, so that is generally, if you did not know the story, everybody will think like, okay, you want the boy to realize, the answer is correct. Like what madam said is correct. The professor, the teacher says, hey man, I also kept my eyes closed. So the moral of the story is that's how, highly the teachers must be placed by the students. They should feel like, okay, so this is we have to be their guidance and make sure that they realize their mistakes in a subtle way. This guy probably realized his mistake, because the professor did it, the teacher did it in a different way. So I'm sure most of you professors and teachers are following similar methodology to keep your students motivated and teach them the right things to do. Okay, great. Hope all of you like the story, and let's get into the class. Okay, so what I'm going to do is I'm going to just start off with the min-max algorithm, which we missed yesterday, and I'm going to show you a bunch of code. So I request all of you to fire up your Anaconda as well as the Jupyter. Just keep it ready. So we will do a little bit of hands-on. So I'm going to talk about min-max. Is the screen visible? Are you able to see it? The PPT?
Yes, sir. Yes, sir.
Okay. So this was one thing that was not done yesterday. So I think I'm better close the video. So this can. Okay. So the min-max algorithm it's used a lot in the game tree, and it is a recursion search. It's a recursion search. I could say that. It's like more used in chess, tic-tac-toe. It's more like a min-max. It's between two players. So what is the concept of a game? When you play a chess or when you play a tic-tac-toe, anything, what is the concept? Can you guys tell me what is the concept? Sudha ma'am, can you please tell me what are the responses? I don't know whether the doctor is there. Can you please help me with the responses? What is the theme behind two players, two people play a chess or a tic-tac-toe or a carom board? What are we trying to do? Any responses? Why are you playing a game? You're playing a chess with me. Why are you playing it? Just don't tell me because you want to pass your time. Other than that, what is it? To win, exactly. To win, ability to think the next move, focus. Excellent. Thank you. Yes, every step. Okay. So, simply put it, you want to win, you want the other person to lose. That's all. That's exactly what this uses. This min-max. When you play, you want the maximum, you want the other to get the minimum. When the computer plays, the computer wants the maximum and wants to give you the minimum. That is the simple concept of min-max algorithm. It uses the depth first search algorithm, and because it goes to the depth, once it reaches the terminal, it will come back up. So this is the key. Maximizer will try to get the maximum possible score, and the minimizer will try to get the minimum possible score for you. Okay, so it's a depth first. So let's take a look at it. This is A, B, C, D, E, F. This is the terminal node. This is where it starts, right? And it goes up to the solution A. So the first is maximizer, minimizer, maximizer. So that's how it works. So let's take a look at this. It starts with maximizer will start with minus infinity and minimizer will start with plus infinity. So the first step is we will apply the utility function to get the utility values. A is the initial state. Maximizer will take the first term and will have the initial value of minus infinity. Minimizer will take the second term, it will have the initial value of plus infinity. So now let's say what happens. For node D, maximizer is going to start. For node D, it will start with 1 and minus infinity. So between 1 and 4, which is the maximum? Because your maximizer is working. Just keep typing because I'm not seeing. I don't know if Sudha madam is there. Can you please tell me whether they are giving the inputs, madam?
Yes, sir. -1.
Maximum.
Sir, Vikas is giving
Maximum.
-1. 4, 4, 4.
Between -1, 4, which is maximum? 4.
Everybody is typing 4.
4. Between 2 and 6? 6.
6.
-3 and -5, which is bigger?
-3. All are typing.
0 and 7, it's 7. So you can see this gets passed on to the maximizer node. 4, 6, 3, 7. Next step is minimizer. Minimizer's job starts with plus infinity and it's supposed to minimize. Before I show the next slide, what do you think will be the values of B and C? I think you can think easy. 4 and 6, minimum of 4 and 6, minimum of 3 and 7. What will be the values? B value, C value. You can do it. What's the B value?
4, 4,3.
4, comma?
-3.
That is -3.
Somebody is typing 4,3, 4, -2.
So the maximizer now, what value will the maximizer take? Instead of 4, it will take 4. So this is exactly how the min-max algorithm works. So this is basically how the min-max algorithm works. So I will take you and show a code. All of you please have Anaconda up and running. So let's go into Anaconda. Before I go into this min-max and water jug, I'll show you the breadth first search. Remember yesterday we were talking about the breadth first, depth first search. Okay, I request all of you to, if you get an error, you will tell me what to do. I'm just going to give the entire code in the chat, and I'm not going to tell you if you get an error what you should do. Okay, let's run this code on. I'm going to run this code now. So this is just simply drawing a graph. Simply drawing a graph from 1 to 2, edges from 1 to 2, 2 to 3, 3 to 4, 4 to 5. Then again 1 to 3 and 1 to 5. So I'm drawing these edges and I'm making these as nodes and I'm just drawing a graph. So just confirm how many of you got. You might get an error. I want to see whether you're able to solve that error. Oh, got it. Okay. So
All are getting
okay.
graph output.
Okay, great. So, okay, super. So you got the graph output. Now, let's see how to traverse this graph efficiently. So I'm going to first draw a graph and then let's create a graph and then we will do a breadth first. There we go. Draw it. Oh, maybe the last portion got cut. Last portion, take it from here. I think after the edge node, take from here. Leave this POS out. Take this. Once you do this graph n equal to x, graph add edge, node edge. Don't take this position because it's half baked. It will error out. Take this from here, position A. So we are trying to import the NumPy network matplotlib, and we're going to just draw the graphs with all these positions for A, B, C, D. We're going to draw. Okay, very good. So you guys are done. So you might have a graph like this: A to B, A to C, C to D, C to E, E to F, all of you. Now you tell me the breadth first search. You learn the algorithm. I'll give you the code, but if I'm going to do a breadth first search on this graph, what can be the answer? It can be wrong also, don't worry. But try to give it.
Lalita ma'am posted A, B, C, D, E, F. Menaka ma'am posted A, B, C, D, E, F.
So let's see whether your answer is
Yeah,
right.
Sheikh sir, A, B, C, D, E, F. Everybody is posting, sir.
Okay, just copy that on the top, leave the for. Copy up to print process. That is not the answer. You run it and you will see and you will understand. And I want you to go through the graph. The answer is on the bottom. A to B. Here. A to B, A to C. Right? Then it will go from, this is done. Then it will go from here. Then it will go to B to A and B to D. Then this is done. Then it will start with C. Then it will go to C to E and C to D. See, breadth-wise it has to do first, and then go to the next node. Are you guys able to follow? Are you guys with me?
Yes, sir. Yes, sir.
Okay. I'm giving this comment so that you can also read those comments later and understand it much better. Great. Error, madam, if you have to just make sure, Lalita, madam, you have to don't copy here, madam, for the for condition, because it's broken here. You can see this. Don't copy this. Go up to processing vertex and then copy from this. Then it will work. Sorry, I should have not given a lot of code because it's not taking it. Even here, let me check before I send it. See, even this is not working. So I will not send this defined part. Let us send the. We just put this comment. Okay, so you can refer it, read it later. So I'm going to give this part. Super, Ajmal. Very good. Then while stack, return path. Very good. And then I'm going to print. So this is depth. So it's going to depth-wise, it's going to go down. So we are defining a function here, graph comma start. We are telling where to start, and then we are giving the parent and the path list. So stacks, all of you know, it's going to use the pop and queue. So when you do a stack.pop, what is ever first in the queue will be gone. Wow, Professor Dubey has already done it. Superb. So it is doing depth-wise, A to C. And then where did it go? It went C to E, E to F. See? C to E, E to F. So it's going in the depth-wise direction. Okay? All of you are able to follow this? Comfortable? Can we move to the next code? Happy? Okay. Done.
Yeah.
Excellent. Excellent. Hi, Doc.
Hi.
All right. So now let's go to the A star. A star is one of the, what I think I should do. Maybe you know what, A star is too big. I'll just send this code. You guys can run it later. Let's do the water jug problem. Water jug is basically, a lot of you might have heard this. This is the problem that we are going to define coming your way. As you can see, the initial state is there are 3 jugs with capacity. 6 liters it can hold. XYZ, where X is greater than Y, Y is greater than Z. That's the jug capacity. So the initial state is there is 12 liters in one jug, 0 liters in another jug, 0 liters in another jug. So your final state should be equal amount of water should be there in at least 2 jugs. However you want to change it, you can change it. So we are defining the capacity as per the rule. Morning, doctor taught you about the rules, right? We are defining the rules here. Maximum capacity of 3 jugs is XYZ. X should be greater than Y, Y should be greater than Z. So I'm saying my jug capacity, first jug capacity is 12 liters, second jug capacity is 8, third jug capacity is 5. So I'm just moving that capacity of 0 X, capacity of 1, 2. So we saw this yesterday, arrays. Remember, this is a list, this is an array. That's why we gave you all that yesterday. Now I'm going to make the memory empty where I can mark where all I visited. Oh, how, madam, you already gave
Dr. Surya.
Dr. Surya already gave you're too fast. Just hold on, madam. Just hold on, Surya. Okay, so this is the next part of the code where it visits answer and you take the states, copy that and paste it. And then let's do the condition one by one, memory, which is of the visited state. So copy this. And I'm going to empty the jug A. Let's copy that part. Then I'm going to empty the jug. See, please make sure that the indentation is like this. Otherwise, you will get an indentation error. So empty the A into C. Now I want to empty the jug B. That is the next part. So I'm going to empty the jug B into A. Next is I'm going to empty the B into C. After I'm done with that, I'm going to empty the jug C now. And I'm going to empty the C into B. And just make sure this is the last piece of the code. This is return false. This we are defining the different rules and conditions. Now comes the real part. I'm going to have you guys done so far? Just confirm. You're done so far. So let's put the initial state. Okay. So this is the initial state. I'm going to say initial state was given to me as 1200. And I'm going to print the state working. I'm going to print the memory. Go up to this part and tell me what you're getting. Do the get all states initial first and then print the memory. Let's see what we are getting. Are you able to get the answer? Okay. Try this. Now ask it.
Yeah, 1200. Some gravity is giving some answer.
Okay. Try, let it print the answer. Tell us what it does. You should be getting a bunch of transactions. Are we getting it? No responses yet. And then finally do this. Are people getting output? There's no response. Am I audible?
No response. Yes, sir. Yes, sir. You're audible.
Indentation error, madam, you have to be careful. You have to make sure that I will anyway share this programs with madam, and she will send it out for your purpose. But see here, as I said, this if condition, this is an if loop inside this, then there is an if inside this else if. This is what is called as indentation problem, madam. So if this else is out a little bit, you will get indentation problem. So make sure that the indentation is done properly. So okay, all of you are getting indentation problems, is it? Okay, fine. So this should be the output. When you run it, it should say that 660 should be the other way around. If you do the print and answer or reverse, it will be from 1201, then it emptied 480, 084, like that. All the different steps will be there, and the final position is there. If you do answer dot reverse, it will print it in the reverse direction. Okay, this also I will share. I will quickly show you this min-max algorithm in operation. So what we are doing is we are creating a game controller with 2 players. Self end player and board player is 0 into 9. I'm going to have 9 squares. And I'm sure all of you know tic-tac-toe, right? I'll explain it. It's quite easy. Then make a move. Does the opponent has 3 in a line? You're going to check. So in the tic-tac-toe here, this is the tic-tac-toe board. You can either have it across or top to bottom or horizontal or vertical or across. Then you win. So it is going to check whether you have it in 1, 2, 3, 4, 5, 6, 7, 8, 9 like that. Then check if the game is over. Otherwise, show the current position, compute the score. So it's a simple program. I'm going to run it. What is the min-max concept? Never allow the opponent to win. That is the concept. If you choose as the minimum, you choose the maximum so that he never wins. So let's see whether the computer lets us to win. I'm going to play this tic-tac-toe game. Oh, you see this? All of you see the tic-tac-toe board? 0, 1, 2, 3. So I'm going to choose a position. You can tell me. So this is, I will play according to you. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. What should I enter here? Participants, tell me a number. You should understand. If I have 1, 4, 6, 1, 4, 7, I win, or across I win, or on the top I win. What should I enter?
We are getting answers 5, 5, 9.
Any one number, madam. Any one number you can tell, whatever they say.
5, sir.
Majority, maximum 5.
5.
5. See, the moment I played it, I put 0 here. See what the computer did? Computer went and put an X here because I put an 0 here and a 0 here, I will win. So the next what should we play? You have to see this and tell me. So I can put 0 here so that I can make this here, or I can put a 0 in 6th column. So there are 2 options for me to win, or I can put a 0 here to get a diagonal. So I'm going to choose 7. I'm going to check this position. So let's see what computer does. Computer, what do you expect if I put 7? Where will the computer put an X? The position, can somebody tell me? 1, 2, 3, 4, 5, 6. I'm going to put it here. Okay. Where do you think the computer will put a X? Position.
3 there.
Exactly. You got it. See, did it. See? It automatically did it. So it is not going to let me win. So now my other option is to put a 0 here or put a 0 here. I'm going to put a 0 in
2.
2 is not. Okay, I can also put 2. Yeah, good. Okay, let's do 2. Oh, so immediately computer went and blocked me. I can't win because otherwise I would have put a 0 in position number 8. So my only option is either 2 or 4 or 6. So let's put 6 because I don't want the computer to win, because if I put here, the computer will beat me. So I'm going to put 6. Bam. Say, there you go. So there is no option. I have to just choose 9. Nobody won. Okay. This is how min-max algorithm works. I will share this code also. You can also try it. So Are you all satisfied? Seeing it in action, seeing the, not only hearing the theory, also seeing it in action? Excellent. That's what we want. Okay, we will definitely share this code, and the subsequent ones we will try to, the fuzzy logic you will be able to do it. It's a small snippet of code. I will, madam, I will definitely, we will share the code. Okay. Now I'm going to walk you through this propositional logic. There were quite a few logics that doctor was speaking this morning. One of them he has mentioned is propositional logic. Propositional logic is the simplest form of logic where all the, madam, break is at 3:30, 3:15, like 3 o'clock. When is the break, madam? 3 o'clock, right? Okay.
3 o'clock time, please.
Okay, done. Okay. Propositional logic is nothing but it's this logic state, simplest form of prepositions. It's English preposition. That's all. It's a declarative statement, declarative statement, which is either true or false. It is a Sunday. If I tell you today, it is a Sunday, is it true or false? True or false? If I tell you today is a Sunday, what will you say?
False. False, everybody.
Exactly. Sun rises from the west, it's a false preposition. 4 plus 5 is equal to 7, false. 5 is an odd number, false. 4 is an even number, true or false?
5 is an odd number, true.
True, correct. 4 is an even number? True. That's all. That's all preposition logic. Preposition logic is a Boolean logic because all of us know, coming from the engineering background, Boolean means 0 or 1. And it also is represented using preposition symbols such as A, B, C, P, Q, R. We will see that it has connectivity, and if the preposition formula, which is always true, it is called as tautology, and it's called a valid sentence. If the formula is always false, it's called a contradiction, because people say you are contradicting me all the time. Statements which are questions and commands or opinions are not prepositions. These are pure English. Where is Rohini is not a preposition. How are you? See, because why do they say this is not a preposition? Where is Rohini? How are you? What is your name? Can you connect this line and the first line and tell me the answer? Why you can't represent this in preposition logic? Exactly. It is not a simple yes or no statement. Very good. Very good. Superb. Okay. So within preposition logic, we have atomic preposition and compound preposition. Atomic preposition is simple. Just a simple sentence which is either true or false. We saw a whole bunch of atomic prepositions earlier. Sun is cold, false. Okay. 2 is less than 4, false. Compound preposition is constructed using simple atomic preposition within parentheses and logical connectivities. It is raining today and the street is wet. Okay, so it's a compound. Compound and is a, when you put and, it becomes a compound statement, right? In English, Rajan is a doctor. Because of that, he's got a clinic in Chennai. Okay, so this is compound preposition. Then negation. Negation symbol is this. Not P is called negation. Conjunction symbol is an and symbol. This is called an and symbol. P, Roshan is intelligent. Q, Roshan is hardworking. This is implied in the preposition logic as P and Q, which means Roshan is intelligent and hardworking. This is called as conjunction. Disjunction, opposite or function. P or Q is a disjunction. Example, Ritika is a doctor or an engineer. Can Ritika be a doctor and an engineer? I can't ask this question here. There are a lot of doctors and engineers here. Correct? This is not a disjunction statement for you guys. For me, it's a disjunction. It's not a disjunction for Dr. Venkat. He's an engineer and he's a doctor. I see a lot of doctors there. So please don't come back and tell me this is a conjunction statement. For you, it is for me, it's a disjunction. Ritika is a doctor and a lawyer. Okay, so like that. Implication. P with a forward arrow Q means P implies Q. If it is raining, it implies the street is wet. So P says it is raining, Q says street is wet. If you represent this P implies Q, you're saying P is implying Q. Biconditional, if and only if condition. If I want to apply if and only if condition, you are alive only if I am breathing. If I'm not breathing, I'm not alive. So if and only if is represented like this. So these are the various connectivity symbols: conjunction, disjunction, implication, bidirection, negation using the truth tables. Where do you think this will be useful? What has this got to do with AI? Can you please just throw your 2 cents? Why do you need this? Rules framing, excellent, exactly. So doctor showed you a lot of knowledge base, taking decisions. Beautiful, that's all. Logic. You guys are connecting. See, the reason why I'm asking these questions is to help you connect. Otherwise, it will be very, very disjointed. You're learning some concept. You know, I'm sure most of you might be doing it. If you employ this kind of a teaching methodology with your students, always try to connect with what they are learning, and also try to connect with real-time examples. Like when doctor was doing, he was showing, like he immediately picks up the phone and shows it to you. What do you see on the screen? What knowledge do you infer? So that will register in the student's mind. Oh, if it is knowledge representation, this is how the robo will see. So try to do that, and it will be very effective. We always follow that. And also try to bring a connect. Then some of the limitations of propositional logic are, if you have to represent all and some. Let's say I want to say all girls are intelligent, some apples are sweet. This is very difficult. Propositional logic is very limited with expressive power. We cannot describe it with less logical functions, because see, the car is going, you want to define an automatic car. If you're using propositional logic, it can say it's A or B. Somebody is coming or it's not coming. If somebody is coming, stop. It won't work like that. You will see that in fuzzy logic. It is fantastic. I have an explanation on how automatic cars work, and also how your automatic braking system works. So it works on inference rules. So it infers based on the evidence and facts, which is based, it's called as inference. That's what knowledge, he was teaching you knowledge. So that is a follow-up to this. Knowledge has got implication. It is a converse, meaning vice versa. Q, P implies Q is implication. Converse is Q implies P. Contrapositive is not Q implies not P. Inverse is not P implies not Q. So these are some of the internal truth table issues which you can always, it's all these logics are inbuilt. So we want you to have a feel of it. That's why we're going through this. See, these are the modus ponens and the modus tenens. You will see is, it's one of the most important rules of inferences, and it states that P implies Q is true, then we can infer that Q will be true. If P implies Q is true, it infers that Q is also true. How? If I am sleepy, then I go to bed. When do you go to bed? Only when you are sleepy. See the statement, I am sleepy, conclusion is I will go to bed. So this is what is called as modus ponens. Modus tollens is exactly the opposite. The rule states if P implies Q is true and not Q is true, then not P is also true. If I am sleepy, then I go to bed is implied by Q. Not Q is what? I do not go to bed. When I am not sleepy. So see, modus tollens will give you the opposite of it. I do not go to bed. If somebody is saying it, you can immediately infer that person is not sleepy. The third rule is hypothetical syllogism. Hypothetical syllogism states that if P implies R is true, whenever P implies Q is true and Q implies R is true. You see the connectivity, P, Q, R, all the three. P implies Q is true, Q implies R is true means P implies R it's cross-sectional. If you have my home key, read, if you look at all these statements, you'll easily understand the rules. If you have my home key, then you can unlock my home. That is, P implies Q. So when can you unlock my home? When you have my key. That is what is implied. Then if you unlock my home, then you can take my money. When you unlock my home, you can take my money. So what does this imply? When can you take my money? When you have my home key, right? You can see this. My home key, you can take my money. P implies R. Yes, any questions? I request somebody is unmuted, so you can. Similarly, we have disjunctive syllogism. Disjunctive syllogism is the opposite. P is true, then Q will be also true. Today is Sunday or Monday, P or Q. Today is not Sunday means what? Today is Monday. I'm saying today is Sunday or Monday. Then the next statement I'm saying today is not Sunday. Obviously, you will infer it is Monday. Okay. So this is also used a lot in machine learning. It is called as one hot encoding. When you have 3 variables, they will only do n-1 variable declaration in one hot encoding. Addition. P or B will be true. I have vanilla ice cream. I have chocolate ice cream. Both are true. So it's an OR condition. Addition. I have vanilla or chocolate ice cream. So this is the famous Wumpus world problem. I'm sure a lot of you are familiar with it. So this is very simple. This is the agent. Venkat taught us about the agents. This agent has to get out and reach to this gold, take this gold and come out. Every adjacent room is a breeze, is a pit or a Wumpus is there. If the Wumpus is there in the adjacent room, the agent will get a stench, a smell, very bad smell. If there is a pit in the adjacent room, you'll get a breeze. So you see this, the agent is here, the Wumpus is here, there is stench. The breeze is here, there is a pit. If he is here, then there is breeze, then again pit. If he's here, is breeze, there is pit. There is gold. If he's here, if he go here, then if he has to only go here, he will die. So he cannot fall into the pit or get stuck with the Wumpus. How does he get out without getting caught? Taking the gold and coming back is what this problem is all about. How does he navigate the cave? Sorry, it's a 4x4 grid. These are all the points: 10,000 point reward points, 1,000 for penalty, 1 for each action, and 10 for using an arrow. Minus 10 if he is using an arrow. The agent initially will start at 1, 1. All of us know this, right? 1, 1, 1, 2, like that, right? So he is going to first row, first column. He is going to start. Then he will randomly move. He has to figure out how to go. So I have told you the rules. So now tell me how you will play this. I told you there will be a stench. There will be a glitter when he goes near the gold. Okay. So how the agent's first step. Okay. So what is he doing? The agent is starting here. The room is safe. Why is the room safe? There is no heavy, because he is starting there. He didn't fall because there is no, this is the starting position. So this is a safe block. Next block, what does he have? He's got breeze. So what does it mean? The adjacent square is a pit. You see this here. P is pit. Should he go here or should he go here? Both are pits. So what does he do? He comes here. He is getting the breeze. So this can be a pit. This can be a pit. So what will the agent do is he'll come back here. He's not going to go because he opens this door. He might fall here or he will fall into this pit. So he's going to come back to his position. See, room is safe. He comes back. He comes back to 2, 1. Then what he will do is now the agent needs to move forward. So it will be either 1, 2 or 2-1. Okay, 2-1 is, he won't move to 2-1 because he knows it's a breeze, so it's safe for him to go back. Third step, what the agent is going to do is, he's here, he's not getting any breeze, so, or any smell. Obviously he knows this is the best bet for him, so he moves to this position. From 1-1 the agent will move to 1-2, right? And also he knows when he gets here he gets a stench, so he knows there is a wumpus here. Here there is nothing, he goes here to the next position. Therefore the agent infers in this room 1-3 in the current state there is no breeze, which means 2-2 there is no pit or no wumpus. Here he's standing here, there is no breeze. Okay, so what he's going to decide is, so this 2-2 is safe, so he comes to 2-2, so it is safe, we will mark it okay, and then the agent moves further to 2-2. So from here he goes here and then he goes here. Then finally once after 2-2, hence there is no stench, there is no wumpus here, and no breeze, there is no pit here. So since this was a pit, he had a problem. So he will move into 2-3, grab the gold. Now tell me, how will the agent come back? He's got the gold. How will you make the agent come back? He's taken the gold now. How will you make the agent come back? That's it. Fantastic. Simple back propagation. That's all. Return path. Wherever you went, come back in the same path. That's it. Simple. So this is the basic way they will go, get the gold, and then come back. Okay. So that is the wumpus. And then on the first order logic, this is another type of logic which is used in artificial intelligence. It is propositional logic. We can represent the facts either true or false. Sometimes it is sufficient, sometimes it's not sufficient, because you might have to represent complex sentences on natural language statements. Say for example, consider the following code, which we cannot represent in predicate logic, propositional logic. Humans are intelligent, or Sachin likes cricket. This can be represented using a first order logic. So we already saw this water jug problem. First order logic is a predicate logic or a first order predicate logic. It is known as both predicate or first order predicate. First order logic is more like a natural language, and it has got facts that can assume the following objects: A, B, people, number, colors, wars, theories. It can understand relations. It can be unary relations: red, round, adjacent, any relations: sister of, brother of, has a color, comes between, father of, best friend. This is like more like a natural language. First order logic has got two main parts: syntax and semantics. So I'll show you in the next. We'll have a syntax and semantics. The syntax of the first order logic is a collection of symbols. When you're writing a statement, you will use a shorthand notation. This is some of the FOL syntax. Constants are 1, 2, variables x, y, z, predicates brother, father. You can also use functions, square root, left leg off, connectivities, equality, and quantifiers for all, for any. Okay, we'll see all this for all. Here, this is atomic sentence that I want to represent in predicate logic. Predicate logic are represented as such: predicate followed by the terms. Let's say I want to represent Ravi and Ajay are brothers in predicate first order logic. How do I do that? Or predicate logic, how would I do that? Brothers, I'll take this, which is common. Brothers, and I put Ravi, Ajay, will imply Ravi and Ajay are brothers. Chinky is a cat. Cat of Chinky will represent Chinky is a cat. Complex sentences are nothing but will have two parts, subject and predicate. X is the subject, is an integer, is a predicate. It's pure English. X is an integer, it consists of two parts. First part is the subject, second part is a integer, which is called, known as a predicate. These are the two. Yes, madam.
Sir, Deepika madam is having doubt. Why the name first order?
Why the name first order? See, here we are trying to order whatever is coming first, like Chinky, that gets ordered. Ravi, Ajay gets ordered, and based on that we are giving this particular meaning. This is what I understood. Maybe there may be other answers. If that is not the right answer, pardon me, because we don't know everything. Because that's how I have understood wherever I read. That's how I understood. I might be wrong, Deepika madam. If you find another answer, let me know.
Actually, if we talk about differential equations or difference equations, straight polynomials, I think that's fundamental is being used.
It could be from the derivatives you're saying, madam. First order derivative, second order derivative.
Yeah. So polynomials, when you go for a polynomials, the order of the polynomial is the order of the particular system.
Excellent.
Or a particular function. Okay. So maybe we are using here also first order logic statement can be divided into two parts. Maybe the logic statement, I don't know how it is being used in the perspective of logic statement. Let me go through the theory or whatever it may be. So I'll try to give the answer by tomorrow if possible. Okay.
Great,
so definitely it must be related with the logic only. So I'll verify and inform you tomorrow.
Okay, thank you, ma'am. So we have two kinds of qualifiers. One is the universal qualifier, another one is existential qualifier. Universal qualifier is for all, everyone, everything. Existential qualifier is for some, at least one. Okay, so this is E for all is represented with the V dash X. Existential is represented as an ulta E. You will see this here. So let's see. Example, all men drink coffee. Let a variable X which refers to a man. So all X can be represented in this EOD as below. X1 drinks coffee, X2 drinks coffee, X3 drinks milk. X1, X2, X3, X4, Xn, man. Universe of discourse. Okay, that's what is called as an EOD diagram. Xn drinks milk. So what we say is, for all X, man of X implies drink X, coffee. So this can be read as there are all X where X is a man who drinks coffee. This is how you will represent in the first order logic. Then you have existential quantifier is there exists for some or at least one. You want to say some boys are intelligent, some doors are open. You can tell the robo some doors are open, some signals are green. You want to represent that X1 is intelligent, or X2 is intelligent, or see that is and this is or. So when it comes here, it goes ulta. For any boys X and intelligent of X means there are some X where X is a boy and who is intelligent. So these are existential quantifiers. Some of the little examples that you need to remember, points to remember is the main connective for universal identifier is for all symbols is implication, means implies. The main connectivity for existential is AND operator. Okay, so examples of FOL qualifier: birds, all birds fly, predicate is fly, birds. For all X, bird of X, fly of X. Every man respects his parent. Respect X, Y, where X is the man, Y is the parent. So you will write it like this: for all X, man of X respects X, parent. So say these are other, some boys play cricket, so we represent this as some students like math. Not all students like both math and science can be represented as for all student of X implies like maths, some will like science. So that brings us to the end of the logic. We will go into the more interesting topic on fuzzy logic. So far, are you able to follow? Are you able to see whether you can apply this in AI, how all this prepositional logic, predicate logic, first order logics are useful. So you can take this forward and start thinking. So when you see a robo related product, you'll say, okay, how is this applied? Why would this be applied? Okay. So now this is a very interesting part of the session. Fuzzy logic is all around us. So far what we saw is pretty much Boolean related. Okay, even though for all men this is, they're including everything. Can you tell me, is there a way to represent is little intelligent, very intelligent, okay, or can I tell the robo that this is hot, very hot, cold, slightly cold? Is there an option so far from what you saw? Is there a way to represent such statements? Exactly, yeah. We have to, we don't have, it's yes or no, it's cold, hot or cold. It cannot say very hot, very cold, little hot, little cold. So there comes the word fuzzy logic. Who do we call that guy? He's a fuzzy character. Who do we call a fuzzy? Do we ever somebody fuzzy? This guy is a fuzzy guy. Complicated, confusion, yeah. Confused, vague behavior, not sure, not 0 or 1 type. So that's all. They just took it, applied it here. So fuzzy logic refers to things. Oh, see, somebody read the screen straight away. Not clear or a vague. The answer there itself. So this is for an event or a process that keeps changing continuously. Cannot always be defined as either true or false, which means that we need to define such an activity in a fuzzy manner. That's what we studied. It's not just true or false. I cannot simply apply for the real world problem. If I'm going to say I want a Boolean logic, it's going to be oversimplification. Nobody will work like that. If you see a robo go from first floor to second floor, if you see somebody stop, it can't. Imagine if I put this 0, 1, 0 logic into a car that I'm going to do an auto driving. If somebody coming is in the middle, stop. That's all. So you said there is somebody coming, you said 0, I'm stopping. Let's say it went and there is a tree or something. So it's slightly figured off. There are so many trees protruding in the road in India. So it goes and sees the tree, it stops. You're creating a traffic jam. It's not a real an issue. So to take you away from that, they have been introduced something called as fuzzy logic. In fuzzy logic, 0 is called as the absolute truth. 1.0 is, I'm sorry, 1.0 is the absolute truth and 0.0 represents absolute false. This is the value in between the absolute truth and absolute false is what represents the fuzzy. So let's take a look at this and you will get a clear understanding. Is Ram honest? If I say true, yes, 1, false, no, 0. Boolean logic, Ram is honest. Based on this previous prepositional, predicate, first order logic, I can never represent extremely honest, very honest, sometimes honest, extremely dishonest. This is fuzzy logic. So this is nothing but probability. Probability values are always between 0 and 1. So I can break the probability of Ram being honest. There people might say he's extremely honest. Some people might say he's very honest. Some people might say he's sometimes honest, extremely dishonest. So I can take this situation and apply this. I'll show you how it is applied in braking system. I'll show you how it's applied in air conditioning system. We will see it. We are going to see a code on how. Yes, madam.
Sir, Ishwari Charan is asking, can we use the fuzzy logic in acoustic signal recognition?
Can we use the fuzzy logic?
In acoustic signal
Yes,
prediction.
yes. See, acoustic signal recognition is, could be a feeble signal. You might have to receive a signal and then you might have to enhance the signal. So you cannot say you hear the signal or you don't hear the signal. It could be you can, yes, absolutely. Fuzzy logic is used everywhere. Acoustic signal recognition is a good candidate to be used. And Madam communication, electronics communication, Madam can also answer that question. She is a better candidate to answer that question than me. Yes, you can, Madam. So this fuzzy logic was introduced, fuzziness was introduced by 1965 by Lofty Zadeh in his research paper. See, you doctors create these things. That's why we want you PhD scholars to come up with such fantastic things. Somebody found out this fuzzy set, and this entire AI works on this now. Today, no fuzzy logic, no AI system. We can all say bye-bye. So Lofty Zadeh observed that unlike computers, human decision making includes a range of possibilities between yes and no. All of us know this, right? When somebody asks something, do we say yes or no? No way. Certainly yes. Possibly yes. Cannot say maybe, I will, I may. Don't we use that? If somebody comes and asks you, do you say yes, I will do it? No, right? You will not. Or all of you say that. All of you are 0 or 1, or you're like what Lofty Zadeh says, maybe, can be. How are you? All of you are just 1 or 0, is it?
We are always fuzzy, sir.
Huh? We're always fuzzy. The participants are not saying anything. Straight away I can see they are fuzzy.
Exactly. Deepika ma'am is saying fuzzy.
Yes, depending on the work given, correct. Certainly yes. So that is what fuzzy logic is going to use here. Implementation is done between small microcontrollers to large microcontrollers, network, workstation, everywhere it is being used. Why fuzzy logic? It's useful and commercial for practical purposes. It can control machines and consumer products. It may not give accurate reasoning, but acceptable reasoning. It helps us to deal with uncertainty in the engineering area. So these are the key things that you need to remember. The 4 main parts of the fuzzy logic architecture is fuzzification module, knowledge base, and inference engine. How does this work is, it transforms the system input, which are crisp numbers, into fuzzy sets. So these are the fuzzy sets that were described. So you will get a 0 or 1. ROM is honest or not. It will break that into large positive, medium positive, small, medium negative, and large negative. You will see this. We're going to see a very nice fuzzy program. All of you are going to code it on a tipping system. Depending on the service and the quality of the food, the fuzzy logic is going to tell you how much tip you need to give that bearer or that organization. We will see that. Knowledge base. Then based on this fuzzification, next is the knowledge base, the stores, if-then rules. That will provide. Morning, Venkat was showing you that if-then rules. Here we are using the if-then rules. Then we just saw about the inference. We saw about inference, right? Inference engine will simulate the human reasoning process by making the fuzzy inference, if-then rule. So this is the rule. How is the inference? So we're going to also, in the program, I'll show you the if-then rules. I'll show you how this inferring everything. Defuzzification module is, see, this computer will only understand the crisp input and crisp output. So I will have to get the input, fuzzify it, get the intelligence, apply the rules, get the intelligence, and defuzzify it. I have to give it again a number based on the 0 to 1. I have to come up with my own, okay, if it is between 0 to 0.5, it is 0, or 0.5 to 1, it has to be 1. I have to decide that and give a defuzzification output, and I'll give a crisp output. So 3 things that you have to remember: crisp input, crisp output, always fuzzy systems. Crisp means 0 or 1. Output is also 0 or 1. Fuzzification will break that into individual smaller between 0 and 1. Rules will be applied and it will decide whether to give it out. So in washing machines, right? In washing machines, I am telling you there is fuzzy system. Can you guys tell me give me an example of a fuzzy? Fuzzy can be related to convolutional network. Convolutional network, not really, Professor, because the way convolutional networks uses neurons, they will not go with fuzzy logic. They work on the concept of weight distribution. We will see that. We will have a very good session on convolutional neural networks. It works on back propagation and the weight distribution. The weights are, that's why deep learning is called as black box technology, where the weights are randomly assigned and you have no control. No, I'm asking about washing machines. Can you give me an example of fuzzy logic in what? Beautiful, Jayapandian sir. Setting water level. Then what option, Dr. Valishri? Solunga. Then the option solunga.
Oh, yes, sir. Depending on cotton cloths or other clothes.
You can, exactly. That's it. That's it. Beautiful. Very good. Thank you.
Welcome.
So with the washing machine, it has made the jobs of the husbands a little easier. Just kidding.
Exactly.
The member functions work on fuzzy sets of variables. So it could be between 0 and 1. So we will, based on the membership function, we will find the degree of membership. Okay, so we will see where it lies in between. So this is, we're going to draw all this in our program. You will love it. So in this membership function is defined in such a way that, see, this is always between 0 and 1. You see the y-axis is always between 0 and 1. The x-axis, you have minus 10, minus 5, 0, plus 5, plus 10. This is negative. Okay, this is small, maximum, medium, positive. So what is that? Large for negative. So large negative because it's minus 10, medium negative, small, medium positive, large positive. So this is an example of a input 5-level fuzzifier. Okay, if I'm using a 5-level fuzzifier with 10 volts to plus 10 volts. So if I'm at 0 volts, it's going to tell me it's small. If I'm at minus 10 volts, it's going to tell me I'm at large negative. If I'm at 10, it's going to tell me I'm large positive. So you can see 5 different values. Okay, are you friends, are you with me so far? Am I making you understand? Are you following?
Yes.
Okay. You're able to follow, right? You're able to connect. Okay. Very few people responding. Others are, am I putting others to sleep? Is my voice sounding like a lullaby? Venkat can sleep. Venkat can sleep. I can't. Okay, great. Fine. So this is how the air conditioner works. We all have air conditioners at home, and you can set a temperature in the air conditioner, and it is going to tell. Now all of you are going to, I'm going to make all of you into a fuzzy system, and I'm going to make all of you answer now. Let's see the magic. The air conditioner has a fuzzy system inside. You set a target temperature. Depending on the room temperature, it will give a command to the controller whether I want heat, cool, or no change. So let's see how this works. First, you have to go with how do you build the fuzzy logic system. Define the linguistic variables, construct the membership function, construct knowledge base, convert crisp data into fuzzy data set, evaluate rules, combine the results into each rule, convert output to non-fuzzy values, defuzzification. So start, fuzzify, infer, defuzzify. Step 1, we're going to define the linguistic terms. So we are talking about temperature. So what are the different linguistic terms that you can talk for a room temperature? Cold, warm, hot. So that can be very cold, cold, warm, very warm, hot. So we have created 5 temperature variables, linguistic variables and terms. Linguistic variables are cold and warm. Yes, madam, any questions? Temperature is this. We are ready. We're going to the step 2. I'm going to construct a membership function. Membership function, I have an absolute truth, false, and absolute truth. I am going to tell you, I'm going to control the temperature from 0 degrees to 40 degrees. If it is 0 degrees, it's negative. Okay, low negative. Large negative, sorry, large negative. If it is 10 degrees, is medium negative. If it is 20, is small. 30 degrees is positive, and medium positive, and 40 degrees is large positive. Okay, I have defined my membership function. Next, this is where I'm constructing the rules. I want you to tell me the room temperature is this. What command will you give? This is the room temperature. I'm going to construct the knowledge base. Room temperature is cold. The target temperature is warm. What should I do? The room temperature is cold, but I have set the target temperature to be warm. What instruction should the fuzzy system give? Room temperature cold, target temperature warm.
All are replying yes, heat, sir.
Heat. That's it. Change heat. If it is cold and the output is cold, there is no change. If it is warm, you want it to be cold, it's cool. So here you can convert this. Right now, the temperature, fortunately in Chennai, is nice and cold. It's not cold, it's cold. It is raining, drizzling, otherwise you'll be sweating now. Without air conditioning, you cannot sit. Cold, it is cold, so no change. If I run an air conditioner, hardly the compressor will run. Let's say, for example, your target is 20 degrees, you set it in your AC. When you come in, it's never going to be 20 degrees. So it will be kind of warm, so it will run cool. So this is how it works. Then you, based on that, you will build your basic rules. If temperature is equal to cold or very cold and the target equal to warm, then heat. If temperature is equal to hot or very hot and the target is warm, then cool. Temperature is warm, then no change. So this is how. Then it will perform the fuzzification. It will obtain the value. See, this is the fuzzification I said. See, the temperature is here. It will try to find an exact value for this in an output variable, and it will send it out. And this will arrive at a temperature. See, this might be a 30-degree temperature, and it will tell the logic will find out the temperature, and it will send out, okay, make the compressor run at 30 degrees. So this is basically how the fuzzy logic works. Fuzzy is used in cooking, where all of us would have this electric cooker, right? When it is done, it goes from cooked to warm. So that is fuzzy. Until then, it keeps working. Washing machines, where you have wash cycles, okay, in between decisions, how much to wash, whether the water is clear, you know, computer senses the discoloration that allows the light to pass. There's a lot of things. This is where, if you are wondering why there are washing machines in the market for 10,000 rupees, automatic washing machines, and there are also washing machines which are selling at 50,000 rupees. What do you think is the difference between these two washing machines? All of you agree with me, right? There are washing machines for 10,000 automatic and also available for 60,000. What do you think? Features, basically the fuzzy. The fuzzy inside is very, very exactly. Krishnakant is on the dot. Hit the nail on the head. It is intelligent, more intelligent. It can make sure if it is discoloring, there are washing machines which will stop and it will start giving information. You know, otherwise you give a white dhoti and the white dhoti comes out with a lot of color from the sari. You don't want that. So let's quickly go through the automatic brake control fuzzy logic system. I'm not going to spend a lot of time. I'm going to quickly show you so that I can take you to the temporal logic. This is very interesting. I want to show you. I don't want to miss it. You will love it. How does the car brake? See the conditions. If the speed is slow, distance is close, brake hard. If the speed is slow, distance is far away, it can put light brakes. This is how you drive, right? You don't jam on the brakes if there is somebody far away. You slowly touch the brakes. If its speed is medium, you're going at a medium speed, the distance is close, you will have to brake hard. If you're going at a very high speed, and even if the distance of the object is far away, you will have to brake hard. Otherwise, you might go and end in trouble. So this is how the fuzzy logic rules are built. And automatic car driving system, we will see how it does. Do you remember hearing this word in this seminar, my dear friends? Arduino. Did anybody hear this?
It is
Exactly. IoT, yes. So see how beautifully this program has been designed. You know, you will definitely have the rest of the IoT session, trust me. IoT sensor is used there. Ultrasonic sensor, motor driver. Then it sends the signals to the servo motor, DC motor. The turning, brakes. This is the exact hardware diagram of an auto car driving system using fuzzy logic. It's being used right now. So this is the ABS. A lot of the cars nowadays comes with ABS, automatic braking systems. So if it is going on a slippy road and you put your foot on the pedal, it will hit you back. So that is called as the ABS system. So it goes through this kind of a logic and sees where to stop. So see here, this is a fantastic explanation of traditional logic versus fuzzy logic. I was telling you, right? If the car is close or far, traditional logic can tell me whether this red car is far away or close. It can never say it is close, very close, far, very far. So the range can be between this fuzziness. Red, 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 light, red, light, red, light, red, blue, light, blue, light, blue, dark blue. So this is how it works. So we also, automatic cars, how does fuzzy logic help in overtaking the car? Overtaking system. How does the algorithm work? First, the vehicle will detect the leading vehicle, check left and right, and check for cars in the lane. If the right distance is more, turn right, else turn left. After turning, move straight until the leading vehicle has been overtaken, return to the original lane. Sir, you are telling me theory. Show me a picture. There we go. There is your picture. So just imagine this. You use an automatic car. The guy in front of you is driving so slow. So this automatic car can't keep using fuzzy logic and keep staying here. It will go this side. It will not go this side. It will probably, like how we drive, slightly to that lane. Okay, there is an object here. So on the right side, there is no object. It comes and then it knows, okay, did I cross him? Then it will come back to this lane. Okay, so this is a slow speeding vehicle and the fuzzy logic comes this side. Okay, some of the advantages is less accidents, decrease in traffic jams, increase highway speed. It's already in use in US, big time. Elimination of traffic, maintenance, feel of driving. Some of the key applications of fuzzy logic is automatic gearbox. It's fuzzy logic. A lot of people don't know. A lot of people are driving automatic cars today. It works on fuzzy logic. Four-wheel steering, four-wheel drives, vehicle environmental control. Even the AC that you're using, there are auto AC controls within cars now, right? Photocopiers, they are full of fuzzy. Television knows. You can tell, depending on the light, it will increase the brightness, right? It's all fuzzy. Microwaves, refrigerators, toasters, air conditioners, name it, it's all around us. Some of the pros and cons, it's always there. You know, there is nothing without an advantage or a disadvantage. There is no systematic approach. It's not very simple to understand, but it's got more advantages than disadvantages. I'll show you this fuzzy code logic when we come back. Are you clear with the? Are you clear so far? Okay, I'll go into temporal logic, see how much we can cover until 3 o'clock. and then I'll cover the rest at 3 o'clock, and when we come back, we will run the fuzzy logic followed by machine learning programs. Okay, so let's go. So we have another 6 minutes. So this temporal logic, temporal, anybody knows the meaning of temporal? Exactly, Professor. Beautiful. Well done, Abhirami. Yes, time. It's about time. Temporal logic. So, sir, so far we saw yes, no logic. Then you taught me to do fuzzy. Is there something I can do when certain things move in stages? This happens, then this happens, then this happens. Can I ask the robot to do this only if this is done? Only if this is done, only if this is done, right? And can there be situations where I cannot make straight away yes or no decisions or even fuzzy decisions? Let's say if I want to represent in artificial intelligence the different states, you're going to take a tea break now, right? Or a coffee break. If you drink coffee, the moment the coffee or the tea that comes and sits in your table, it's at one state. From 3 to 301, it's another state. 302 to 303, 304 to 305. Every minute, every second, the state changes. Do you agree or not? Yes, excellent. So now tell me, applying the temporal logic to you as participants, from when you arrived on Monday morning to where you are today, Tuesday afternoon, can you be represented in different states? Are there any different states in your knowledge? Do you agree? Are there, or it is the same? No change, sir. It is exactly how we came in here. Beautiful. That's it. That's temporal logic. This is what I'm saying. Connect with real-time examples. You will never forget. Temporal logic, I'll never forget. I'll always, if there is a confusion, I will connect with my tea. Is the tea the same? Is it hot? No. It has changed the state. Can I go back to the state? Yes, maybe. You may have to go back and heat it up. That is exactly temporal logic. You remember that and you will enjoy these slides. You apply that, you will enjoy the slides. For example, if I have to represent in a proposition, I am always hungry. I will eventually be hungry. I will be hungry until I eat something. It is impossible. You cannot do that. For that, you will need to represent that using temporal logic. You can conveniently and easily represent them using temporal logic. Temporal logic, the applications of that are widely used in formal verification, where it is used in hardware and software systems. The previous state has to be verified before it moves. When you do an installation, when you ran this, simple, you saw temporal logic in action when all of you ran the pip install. What did it do? Can someone tell me the temporal logic that was involved in the pip install? First, what did it do? What did it do? First, what it does, it goes and checks whether that module is there. Then it starts downloading. Excellent, sir. Sangamesh, sir. Excellent. Download. Then it downloaded it. After that, it started installing it, and then it gave you the state changed. See, it's used in software right now. You'll be amazed to see, all of you use elevators, right? All these big apartments you live in, you use, yes, progress of file download, sir. Correct. You have elevators. We will see how elevators, temporal logic is used, how automatic train gates uses elevators. Okay. So let's see a quick example before we go for a break. Consider the statement that I'm hungry. Though its meaning is constant in time, but the statement's true value can vary. Sometimes it is true, sometimes false, but never simultaneously true and false. Are you always hungry? No. Maybe you are hungry at 1 o'clock. After you eat, you will change. Is there a possibility that I will stay hungry forever? No, not really. Don't tell me that this guy doesn't have money, so the pauper will always be hungry. I'm talking about a normal situation. There is a possibility that eventually I'm no longer hungry. I was hungry, I ate food, I'm not hungry anymore. My state changed because I was fed. So it can be sometimes false. The statement can be false sometimes, sometimes true, but it can never be true and false. I cannot be hungry and I cannot be hungry. I cannot be I'm hungry and I'm not hungry. Both is not possible. Okay, so this is the coffee example I gave you. The temporal logic is good for describing static conditions, adds temporal operators, linear time and branching time. Temporal logic's basic idea is truth changes over time. When things are true, not just what is true. Okay, we will use this PTLs. So when you come back, Sudha madam, we can go for a break. It's 3:02.
Yes, sir. Yes, sir. It's 3.
When we come back, we will start with the temporal logic. And I request all of the participants to please fire up your spider. Yeah, all of you can go for a break. I'll just answer Dubey's question. Professor Vikas, it is time series analysis is a part of machine learning where will be
somebody
predicting future.
Hello.
Yes, ma'am.
Somebody was asking for first order and second order, isn't it? So
yes,
what they say, actually they are assuming your data as a set theory. So if you assume the data as a single set, and if this particular set is having data for one variable, only one variable, that is x is the variable, all the data refers to only the age of that particular person, different persons, then it is the first order. And for example, the same set is going to have data of x and also some relations with the x. Like you have x, then you will be having x plus 1 or x plus y, one more variable. You will be so if you have some relations. So if that particular data set is having x, that is only one variable, or an additional this variable with relation of related to some other variable and that function. So if that particular function is going to produce one more data, if these things are all put together in one particular set or a data set, then it is called a second order. Similarly, if the relationship is, if the relation between this variable x is going to be more than one relation, then you can go for a multiple order also. So this I gone through that, and I'm giving you. And one more thing, there was a question about whether fuzzy can be applied to the acoustic. Yes, fuzzy can be applied to the acoustic wherever we have a noise factor which is being introduced in the acoustic signal, and the noise is not known noise, it is unknown noise. So we don't know what type of noise is being introduced practically. So when we discuss about the noise in the acoustic system, definitely we can use fuzzy logic in the acoustic system.
Excellent. Thank you very much.
As far as I know, I have informed. Then you can do some further study also. There are a lot of papers related to the fuzzy logic being used in acoustic noise. Okay, so that you can see so many papers.
Thank you, madam. Excellent.
So it means, yes, we can use fuzzy in acoustics.
Thank you, madam.
Thank you all.
Thank you. Professor Vikas, if you are still there, I can answer your time series question, or I can answer when you come back if you're not there. Okay, you are there. Okay, Professor Vikas, it is the time series analysis is predominantly used for forecasting. So if you give me a data of the last 4 years, I can predict for the next 12 months.
Ranga, are you there?
My sales. Yes, madam.
Hello, Ranga.
Yes, madam.
That is explaining.
Oh, he is explaining now.
I'm explaining the one that madam. So that is what time series analysis is. What Professor Vikas? It is used for future predictions. You can give for another. Yeah, you can use it for weather prediction. Everything, all weather, stock predictions, right? it is there in machine learning, and you also use in deep learning using RNN and LSTM. There's a big. We're going to show you this time series prediction in RNN, predicting the next number as a part of the thing. Okay, thank you. Brother Ravi Ramu, where X is considered to be brother. Correct. Correct, madam. Yes. Sri Lalita, madam, that is correct. Yes, madam.
I hope my explanation about first order and second order was
perfect.
Okay. Okay. Thank you. Thank you.
I'll just go get some hot water and come.
Sir, we'll have again by 3:15, sir, sharp.
Vandara, madam, Vandara, 10 minutes.
Okay, sir. Oh, okay, sir. Okay, sir. Thank you, sir.